Welcome to part 2 of the chapter on aminoglycoside dosing and drug concentration predictions. In this video, we will calculate pharmacokinetic parameters based on measured concentrations after a known dosing schedule when the concentrations are measured in different intervals as trough, then dose, then peak. I hope you enjoy the video. Let's now move into patient case 2 of aminoglycoside dosing. In this case, we have a 75-year-old female patient who's given 120 milligrams of tobramycin every 12 hours as 30-minute infusions at 10 a.m. and 10 p.m. A steady-state trough measured at 9:30 a.m. is reported as 3.6 milligrams per liter, which is considerably above the trough concentration desired, which is usually about 0.5 to 1.5. And a peak concentration measured at 11 a.m. is reported as 8.2 milligrams per liter. What we'd like to do now is determine the patient's half-life and volume of distribution. Here are the measured concentrations, and you can see that the trough was drawn before the dose at 10 a.m. and then after the dose was given and allowed to drop for a half an hour, the peak was drawn. To determine the elimination rate constant so we can get half-life, we would like to use this equation, K equals the natural log of Ci over C divided by time change. However, to use this equation, both concentrations must be in the elimination phase after the same dose. That means the trough would have had to have been drawn in this interval or the peak in this interval. So what do we do when we have steady-state concentrations drawn as trough, give a dose, and then peak? Well, the first thing we need to decide and understand is that at steady state, the rate in equals the rate out, and it's assumed that one curve could be laid upon the next curve in the dosing interval. So what we would assume then is that the peak in the previous interval would be the same as the peak in the next interval, or the trough in the previous interval would be equal to the trough in the next interval. We see that the peak was drawn at hour 1 in the interval, and the trough is drawn at hour 11.5. That gives us 10.5 hours between the two concentrations, and that's what T delta, or the time between Ci and C, would be if we transfer the peak from one interval to the prior interval. So let's do the calculations. Again, K equals the natural log of Ci over C divided by time change, and our values were 8.2 milligrams per liter for the peak and 3.6 milligrams per liter for the trough, and the time between those two would be 10.5 hours. Remember, the actual time between the two was 1.5 hours, but they were drawn in different intervals. This gives us a K of 0.084 hours to the minus 1, and half-life is 0.693 divided by K, with a final half-life of 8.27 hours. Next, we need to determine the volume of distribution. Again, to determine the volume of distribution, we need the equation that describes the dosing approach that's used. In this case, we're going to transform the V over to the left side of the equation and the C into the denominator on the right side. Everything is known in this equation except for volume of distribution, and we have two concentrations measured at two different times after the end of the infusion. So let's plug the numbers in. If we use the concentration of 8.2 milligrams per liter, it's important that we use the time after the end of the infusion that was drawn, or 0.5 hours. If we plug 8.2 in and the 0.5 hours, the volume of distribution is reported as 21.64 liters. The question now is, what should be done? The peak is about right, but the trough is much too high. This indicates the need to lengthen the dosing interval, which will then require a larger milligram dose to create the increased difference between the peak and trough that is necessary. We will solve that in part 3 of aminoglycoside dosing.